Welcome back. Today we're going to be going over some more kinematics problems. Now these problems are going to be a little bit more difficult and a little bit more representative of what you might see in your own coursework. So we have a flower pot falls from a windowsill 25 meters above the sidewalk, and A, how fast is the flower pot moving when it strikes the ground, and B, how much time does the passerby on the sidewalk below have to move out of the way before the flower pot hits the ground. So, as always, let's check our prerequisites. The acceleration does appear to be constant because we know that when something is in free fall, we know that there is one force acting, which is gravity, and that the acceleration due to gravity near the surface of the Earth is 9.8 meters per second squared, and that is a constant value. Now we're assuming that the air resistance is negligible and that there's no other forces acting. Now this is generally a good assumption that there is no other forces acting and air resistance is negligible, just because it's not specifically noted in the problem. However, it is always important to read the problem carefully, just in case there's another caveat or your professor or teacher is trying to trip you up. So just keep an eye out for that. So, we do see that it is in one dimension, so we can assume that these prerequisites are met. So let's go ahead and look at our formulas. We have the final velocity, initial velocity, acceleration, and time. Doesn't seem like quite the right one to use because we don't know the time. We have the final position, the initial position, initial velocity, time. Oh, there we go again. We can't really figure out time yet, so let's go ahead into the next one. We have the final velocity. That's good. That's what we want. The initial velocity, we know that's 0 because it was initially at rest. We have the acceleration. Well, we know that. That's gravity acceleration. So we 9.8. And we know the distance between the final and the initial position, which is about 25 meters, because really that's only the distance between the sidewalk and the windowsill. So this does appear to be the correct formula to use. Now, before we start, it's always a good idea to define our coordinate system, so let's go ahead and draw that out real quick. For this problem, I'm going to define up as negative and down as positive. Now, this is because the problem gives us both velocity and acceleration are going to be pointing down because obviously the acceleration due to gravity is going to be towards the ground, and the velocity, it's going to be falling towards the ground as well. So this is just going to help us keep track of signs easier and just make it a little bit simpler. So I've defined positive as down, so let's go ahead and start plugging things in. Now the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by x or y final. It really doesn't matter, again, as long as you're consistent. There we go. Okay, so we do not know the final velocity, so we'll just leave that there. And the initial velocity, we know that's 0 because it was falling from rest. Now 2 times the acceleration. Now we got to check our signs, but we do know that the acceleration, if it's down, which it is, it's going to be positive, so we can just do 2 times 9.8 multiplied by the distance between those 2 points, or between the windowsill and the sidewalk, which is 25 meters. So now we're just going to continue simplifying. We have the final velocity squared equal to 2 times 9.8, which is going to be 19.6 times 25 we're going to have 19.6 times 25 comes out to 490. Now, we're not quite done because we still have the final velocity squared. So if we just take the square root of both sides, we're left with the final velocity is equal to the square root of 490, which comes out to about 22.14 meters per second. Now this result does make sense because we have defined our coordinate system such that down is positive, so it will be a positive velocity even though it is going down towards the ground, and it hasn't been traveling for too long, we're assuming, because it's been 25 meters or less, but it still has accumulated a decent velocity of 22 meters per second, so that does make sense. So now on to B. How much time does it take for a passerby on the sidewalk to move out of the way before a flower pot hits the ground? So this is going to take a different formula. So we'll back to our list. We have time in both of these, so it's most likely going to be one of these. Now we do know the final velocity, we do know the initial velocity, and we do know the acceleration. So it does look like the first formula is going to give us everything that we need. So let's just go ahead and get rid of some of this stuff here. Give ourselves some more room. So we know the final velocity, initial velocity, acceleration, and time. However, this isn't solved for the variable that we want. So if we were to just rearrange this, we could take the velocities on the same side. The final velocity minus the initial velocity equals the acceleration multiplied by time. And then if we wanted to get time alone, we could just divide both sides by the acceleration. So the time it would take for the flower pot to get from 0 meters per second to 22.14 meters per second, or our final velocity, is just going to be this time here. So we'll just rewrite it. Now we're back to the just plug it in and get our answer. Final velocity, we'll use 22.14 minus 0 over 9.8 meters per second squared. Now, one note is that I did use the rounded version of the final velocity, which will leave some uncertainty in your answer and may produce a slight error. Now, for my purposes, it's good enough. However, I would recommend that if you need a high degree of precision, that you do use the full version or the square root of 490 instead of this 22.14. That'll give you a slightly more accurate result. So calculating this out, the result we get is 2.26 seconds. So the time that it takes to get from the windowsill 25 meters up down to the sidewalk is 2.26 seconds. So that passerby on the sidewalk below that falling flower pot has just about 2 seconds to get out of the way. So that wraps it up for this problem. And let's see if we can squeeze in one more problem. So, we see an archer shoots an arrow at an angle of 43 degrees above the ground. The initial velocity of the arrow is 13 meters per second. Now, what is the maximum height the arrow will reach? So this is a little bit more complicated and a little bit more of a complex problem. So I always find it helpful to draw out the problem to decide whether or not we can use kinematics, and if so, how. So we can say that this dot here is the archer, or if you want to imagine it being a cannon, or really whatever you want to imagine that helps you understand it better, that's just fine. So, and then we have the ground here, and then about 43 degrees would be pretty close to that. That might be overshooting it a little bit, but that's about the angle that we're looking at. Now, maximum height would be just the y component. And the 43 degrees is a mixture of y and x. Now, this may make you think, oh, we can't use kinematics. However, you can. You just have to do some things first. You have to split it up into x and y components. And as always, we have to check, is the acceleration constant? Yes, it is, because in the y direction, the only force acting, or therefore the only acceleration acting, is gravity, which we know and is constant. And in the x direction, there is no acceleration, surprisingly, maybe, but there is no acceleration. So really, without air resistance, that x motion, that x velocity, is constant the entire time, and therefore acceleration is 0. So in the y, either way, the acceleration is constant, and in the y it is 9.8 meters per second squared, and in the x direction it is 0. So our prerequisites are met, and we can move on to actually solving this. So let's make our coordinate system. We have up is positive, down is negative, and as we're going to be focusing just on the y coordinate system at the moment. So how do we break it up into x and y components? Well, I always recommend drawing a triangle. So we have here our vector of 43 degrees above the horizontal. So we can draw a right triangle here with this angle here being 43 degrees. Now next we have to figure out which trig function to use. So we can use either sine or cosine, and we just have to figure out which one would be ideal. Now we do know the hypotenuse of this triangle, which is going to be the magnitude of the original vector, which is 13 meters per second. So we can figure out which one of these sides we want first off, and it does look, since we want the y component, that we want this opposite side. So going back through your maybe geometry or trigonometric studies, we have sine is equal to opposite over hypotenuse, which is SOHCAHTOA, or so. So that does seem like the one we want to use, because we do know the hypotenuse already, and we want to know the opposite, so looks like sine is our function. So we know that sine of 43 degrees is going to be equal to opposite times, if we multiply it by the hypotenuse, because if it's opposite over hypotenuse and we multiply both sides by the hypotenuse, then we have the opposite or y component of that vector here. So we can just plug in what we know, which is 13 times sine of 43 degrees is equal to the v, and we'll use a y subtext. So next we